So turnover.
Speed.
And
Like,
oh,
Yep.
sorry.
And good there.
and stay.
Yep.
Another word marker.
Call it. Action.
And Drive to Survive, season 4. Oh, you've made my day. You've made my day.
Hi there, how are you?
Wonderful.
Are you lying?
Am I lying?
Closer to me.
I will. I'm just easing into it myself. Okay, I want to start a little bit about you.
Okay.
How'd you get, why? Why did you get into science?
Why did I get into science? I didn't, actually. I started off as an engineer. So when I was like 14, 15 years old, I would be taken out of school to do various engineering competitions. So I obviously was good at maths and physics. Went to university to do engineering. And in between that, I'd done extra classes because I'd already accepted into university. So I did extra classes to do biology. And as soon as I started doing engineering, I realised that biology was my true love. Very difficult decision to make when you're 17, 18 years old to drop out of university, to the horror of my parents, I think, because it was, they just thought I would never go back. So I had a paper round and I went back to high school for a year and I went on the dole. And it was the best thing I ever did, because then I went back and did biology, and I was interested in disease, and I knew that maybe I wouldn't make as much money, but that wasn't exactly what I was interested in. I needed to love what I did.
Sorry, Stu. Sorry, mate.
It's all good.
Oh, we're going to go on camera.
So we've got none of that?
I've recorded it, but it's not on camera. Sorry. That's my bad.
It's all good. All good.
Should we start again?
I think we should.
Yeah, I waffled there anyway. I can, just ask the question
And
again.
then we'll start again.
So we're going to go on a Sunday.
Yep.
Cutting.
Cutting
I
that.
did waffle, didn't
You get to pull them.
What are you on then?
I? No, I done it once. I'm good.
How long have we ever got it?
Season 7.
Well, you know the question.
Say it again so then I'll answer it.
Okay. Why? Why did you pick science? How did you end up there?
Yeah. So I guess I didn't start off as a scientist. I started off as an engineer. So for a very young age, I was doing competitions in engineering and taken out of school, which was great fun. So having those challenges of engineering challenges, I thought that was my kind of area to go in my vocation. But once I started university, I'd done extra courses in biology and realised that that was my real passion. To the disappointment of my family and my friends and everyone, I kind of dropped out of university very young, around 17. And I really wanted to do biology and really wanted to work on disease. And I knew I wouldn't make the money, and I was constantly told, you will not make money being a scientist versus an engineer, but I didn't really care. So I worked on the dole. I was on the dole. I worked as a paper boy for a year, and it was a great time to just grow up and actually realise what I wanted very early on. And then as soon as I did science, university was a completely different ballpark. Didn't find it very hard to study compared to doing engineering, which seemed a bit too focused for me. I like a bit of wild, what happens here, what happens there, and there's no real answers. So that's why I did science, and loved it, and it was the best thing I ever did, I think. But from a young age,
What was the attraction? What was the...
I just think, not to play against building a bridge or building a skyscraper, etc. Just your natural fascination of how my own body works or how our body works, and the fact that you can attack diseases, I guess, and maybe change lives as well, which sounds really cheesy, but
No, it's true.
ultimately the real attraction, even though I'm talking about that engineering work, was at 14 years old, imagine imagine not having to go to school every Thursday and be given a challenge that no one can do and actually say, you need to work on this for 4 or 5 months and then you compete at a national level. I just loved that, and I thought, that's not work. And I think that's what science is. I don't think I've ever come to work since I've done science, right? It's a bit of a hobby, right? It's a very difficult hobby, and the challenge is very difficult, or the challenge is, but I really enjoy that, and I love the working in a team. That sounds cheesy again, but
Well,
if you've got the,
why do you like working in a team?
because I think that there's things that I know I can do, and I love that other people can bring completely different aspects to a problem. And I think from that young age, I learned to kind of open up, and you take your ego out, and someone can do the genetics, someone can do the imaging aspects. And so my team now has all these capacities. And so we may have started off as an imaging group, but there is no technology or technique or area of science that we wouldn't dare touch. And I ended up coming back to the whole physics anyway, because the imaging involves very advanced physics. We use multiphoton microscopy. We use techniques where we look at fluorescent jellyfish and reading out how drugs work, etc., and how often they work at subcellular level. So the physics and the maths was still there. It was just, how am I applying it in this disease versus how I could apply it in other diseases. So I just love the whole teams together, and there's no answer. I like the fact there's no answer, and it's like, can we move forward? Can we move our knowledge? And can we move for new treatments?
Explain, what do you mean there's no answer?
Yeah, I guess if you've got a goal, which is to make a skyscraper or to make a bridge, you can make beautiful bridges and beautiful skyscrapers, so there's really no answer there as well, I guess. But for me, it's like to wake up every day and say, well, we're going to have to look at cancer, and some of the most deadly cancers that my team work on, like pancreatic cancer, completely ignored for many, many years, just too hard basket, and nothing changed for like 4 decades. So when there's no real answer to this and no one's going after it, that's definitely a wonderful place to go. It's low-lying fruit, because any change that you find, you can actually really make an impact. The survivals in that disease were around the 4 and 5% when we started, and that didn't change for like 4 decades. That's a disease that we need to look at. In pancreas cancer, the biggest problem there is it spreads so fast, and you get diagnosed at such a late stage. So my PhD, I guess, was all on cell migration, how cells move, understanding the fundamentals of how a cell adapts its cytoskeleton. So each cell has its own little kind of skeleton like we've got, and it adapts that and it allows the cells to move. So if we can understand that, we can target it. And really, lots of people now die of the metastatic disease rather than the primary tumour. And again,
No, you have to explain that. Sorry.
so for example, in breast cancer, as a kind of example, people who die of breast cancer, for example, it's not the primary tumour that actually kills. Sometimes that's been treated or surgically removed. It's the fact that it's spread to vital organs. And so in some diseases, some cancers, it's the spread. So we can't ignore it. It's very difficult to target, and it's very difficult to stop that spread, but it makes a big difference. And so I think we need to kill the cancer, which would be wonderful, but sometimes you have to do both, kill it or contain it. And I think that's the reality of some cancers in the future, and that's where we'll get to, which is maybe, are we going to have a silver bullet for cancer, or are we going to have, like how we used to look at HIV, for example, can we actually treat this disease or manage it, or do you die with the disease, And I think for some we can cure, and others I think we might be, you've got cancer, that's my idea in many, many years from now, that we might not die of cancer, we'll die with it. And so I think that's
That's what I've heard about prostate cancer and
yeah.
prostate cancer. Yeah, it doesn't kill you, but you'll die with it. But that's the philosophy now. It's all about managing it, isn't it?
Yeah,
There aren't really any king hits.
Well, I mean, some of them are quite phenomenal, and
Sorry.
immunotherapies are making massive inroads. But in pancreas cancer, those cancers are classed as cold cancers versus hot cancers. They're immunologically cold. We don't know why the immune system's not getting in there. And so immunotherapies are not really working there. So that's what I mean by we don't know the answer. We know what the challenge is, and one day we'll find out why they're cold. Can we switch them to become hot? And then we might make a massive change to that disease. So that's what I like about the not knowing and the ability to wake up in the morning and not have a specific set goal. And quite often some of the best ideas come in a taxi or when you're out for a run or when you're literally not thinking about work. And work doesn't start at 9 and finish at 5 if you're a scientist. It never finishes really, you know.
What's immunotherapy?
Like I think the simplest way is normally our body is sending out signals to say, for example, I am me, and tell my immune system, back off, this is me. The problem is that in cancers, the cancer stems from us, and so quite often it can still send that signal out to say, yes, I have mutated, yes, I am growing, but according to the immune system, you know, it's cloaked in the fact that it's still me, so please don't attack me. And so now the idea is to actually to switch those signals off, and so the cancer itself then can't say it's me anymore, and your immune system will then start hopefully recognizing that cancer. The beauty of that is, unlike a drug, I guess, you can detect that cancer, then the immune system goes away, builds up, and comes back, and it will hunt that cancer, even if it's coming up, and as I said, for those metastatic sites, it will still recognize that that's now cancer in those different sites. And so it's been really amazing in some diseases, such as melanoma, but not so much for pancreas or breast, but we're going after it for many diseases.
I've got no idea, but yeah, I just wondered. That's part of the mystery, isn't it?
But it's training our immune system to recognize that, and then once it's got it, we'll have that memory and it can go after it again. So even if there's a undetected level of tumour, your immune system remembers, just like any other situation your immune system remembers.
Is there any examples of that working recently? Or?
Yeah, so in melanoma it's quite amazing,
Yeah.
and a few other cancers. But as I said, we work in mainly pancreas cancer and it doesn't work there. But we're doing lots of other different ways of looking at cancers as well. So for example, there's a technique called CAR-Ts, or you can actually train the immune system to actually go after specific molecules that are expressed on the cancer. Almost like when you let a dog smell a rag and then go and find the person that you're looking after, practically the same as that. That's very expensive, very difficult, but we're doing that in prostate cancer as well. It works fabulous in blood cancers, I guess, but in solid cancers, not so much. But again, that's our new area that we're trying. And again, I'm not an expert in that, but working with experts all over this country, we got together and we've got what's called a synergy grant, where you take experts from mathematics, immunology, imaging, different cancers, put them all in a room and say, what would that team come up with that your so-called experts in the area might not, because you'll think differently, right? A mathematician or a physicist will completely think differently to someone who's worked on, say, prostate cancer for decades. They'll have to learn, and sometimes they come from completely different angles. So, love to do that.
Okay. What's the thing you're going to show us a bit later? And why?
And why? Yeah, so in pancreas cancer, so let's just think of a cancer in kind of two ways. So you've got the cancer cells themselves, which for 4 decades we have been smashing them with chemotherapy. Let's go after the cancer. And we've completely ignored the surrounding tissue, right? And in pancreatic cancer, we've got this kind of dense tissue called fibrotic tissue, which it's almost like lots and lots of collagen, imagine, surrounding a tumour. The tumour actually keeps building this up more and more and more, and so you can't actually deliver your drugs to the cancer. So if we go in and just try and smash with chemotherapy and just aim purely at the cancer cell itself, another thing that happens is the cancer cell then builds more and more of this barrier, and so you actually can't get any more drug in. So we've completely ignored this, and even as short as 12 years ago, when we took a tumour, we would see this stuff, smash the tumour up, get rid of that stuff, the fibrotic tissue, and then sequence the cancers and say what's going on in the cancers and what can we do. Within the last 10, 15 years, we've realised we can't ignore that. And actually this is a potential brand new reservoir, I guess, of new targets. So what our group has done, and many around the world now, are before we target the cancer, let's target this tissue that's almost like its Achilles heel. It's protected itself. So if we go in and now reduce that barrier just for a week, and then every time we give chemotherapy, we just do a little pulse to try and reduce that fibrosis before chemotherapy, we can see significant changes in response. And so the cancer cell itself is not protected.
Mm-hmm.
The cancer cell also needs this dense collagen tissue to actually attach to and start running and spreading. So you've got a dual target. So you're now stopped. You've improved the chemotherapy, but you've also not given it something, or a branch, as it were, to start traveling to the liver and traveling to different areas. And so you're stopping the spread, but you're improving the response to chemotherapy. And so we've done this a few times. And again, this comes back to the physics and biophysics. If you get rid of this tissue, this fibrotic tissue, or the normal collagen, your pancreas isn't going to function, right? I mean, it was there for a reason. It's just far too much of it. So we now need to know how much is enough and how much is too much. And so that's why we use advanced imaging inside a live pancreas on a daily basis to say, when we target this fibrotic tissue, how much is enough to improve chemotherapy and how much is too much, because we want to actually almost normalize the pancreas back to its normal function. Then the chemotherapy works, or it can also affect immunotherapy, so immune cells can get in and attack those cancers, but again, it can stop the spread. So that's what we'll show you today. And what we do is we combine cloning and genetics. So if you can imagine a jellyfish, you've seen movies where jellyfish are green or they're red or various other colours. If you put the molecule of interest that's causing cancer in between green and red, when the green and red kind of fluorescent...
Sorry, what was that molecule of interest?
So the molecule of interest, say, could be the thing that's driving the cancer.
Okay.
So what we've got the ability to do here is you've got a green part of a jellyfish, it's called green fluorescent protein, for example. When these come together, you can actually see a change in colour. But we can see this not only at the single cell level, but even subcellularly. And so we can watch when our drug is getting to the cancer, how long it's there, and have we targeted the surrounding tissue enough. And so we can actually fine tune how this works. So we start this with very advanced models of the disease. So we have mice that have the same genetics as a human, and then they've also got these, every single cell in that mouse glows in the dark, and we can actually put, we can look deep inside the abdominal cave and actually be able to see the tumour responding, and that's never really been done before.
It's astonishing.
And we do it we can do it in the colon, we can do it in the liver, we can actually watch cancer cells. It's called extravasate, or spread to that secondary site. And again, those are vulnerable times when the tumour is spreading around the body. Most of it dies, most of it can't make it. And so if we can just manipulate enough, we can actually hopefully stop it spreading. And so that's what we'll show you today downstairs. And between myself and Tree Fan, he's an immunologist, I'm a cancer guy. Between us, we come at different angles. And so I think you guys have seen that before today, that Tree goes deep inside bone. I'll go deep inside the abdominal cavity. I do molecular imaging, and Tree does completely different types of deep imaging. So he goes deep, and we go fast. And sometimes both of us need each other to go deeper and faster. And so we've done this for in cancer they call it the hallmarks of cancer, right? There's about,
I was about to ask, how many hallmarks of cancer?
right, so there was 10 yesterday, there's 11 today, there's probably 12 tomorrow. It just keeps changing. But these are vulnerabilities or classic things that cancer co-ops and uses to grow. So metabolism, for example, or how they divide. There's just so many different aspects. So when I started this, I had a crazy job at AstraZeneca, which was blue sky research. So again,
You'll have to explain what blue sky research is.
I'll explain that now then, is again, it was a job, but there was no real aim. It was, what can we do, rather than measuring a tumour and saying it's bigger or it's smaller or it moves, what can we do more advanced to actually understand the molecular aspects? And so that's where we started using these fluorescent called biosensors to look at different hallmarks. So I think I've got about 12 or 11 different biosensors now to look at different hallmarks of cancer. And we've published those, and many of those have shown that we can combine various drugs to target that specific hallmark. And there's many that we still need to make. So I like the idea that there's hallmarks, but those hallmarks keep getting more and more, and that gives me more and more of a challenge, or our team to more of a challenge.
How did you set up your lab?
Yeah.
And was the ACRF of any help? Or?
So I set up the lab after making some of these mice. I realised that
Sorry,
so these biosensors are genetically cloned into mice that have cancers. We then put these biosensors into human samples as well, which was quite an achievement. So I guess you could imagine it like an avatar. So you can go to surgery, you can take a patient sample, and we bring it back here to Garvan. Within 50 minutes, we've got that growing here in the lab, and then we can try and make them fluorescent. And again, we can now start doing our treatments on actual avatar versions of patients to actually start saying, does our combinations work? So we started that as soon as I got here at Garvan with these biosensors. No one had really done this kind of work before, so that was really exciting to start a lab that I guess looked at cancer in real time. So the easiest way to explain that is, for years we've just been taking snapshots, and if you took snapshots of a movie and tried to imagine what happened, you've got no chance. But if you can actually make a movie and actually watch the entire process in a very unbiased way, doesn't matter what the textbooks say, if you're just watching the process, watching the tumour grow, watching it respond to various therapies, you might well see a vulnerability, and that itself is a beautiful way of actually attacking a cancer that has been kind of overlooked for many years. So that's how I started the lab.
That's the central philosophy.
That's the central philosophy of watch and learn, or seeing is believing, right? And we've got various grants now where we've actually taken human patient samples, we've decellularized them. So if you imagine a tumour, cancer cells, little fibroblasts that create all that fibrotic tissue, blood vessels, nerves, everything you can imagine. We can actually get rid of all of that, right? Using a kind of various types of detergent. And then you're left with just the scaffold, just the architecture that cancer surrounded itself by. And adjacent to that, you can see what the normal pancreas would look like. And then we can just go in and say, what molecules are in the cancer versus the normal tissue? And then from there, we've now got hundreds and hundreds of brand new targets that those cancers secrete, because they want to live on. And I guess it's also quite often called oncogenic addiction, or the cancer itself becomes addicted to this surrounding, and we've kind of ignored it for many years. So there's various molecules that lots of cancers really love to surround themselves by. Might help them grow, might help them move. And so that's what I'm really excited about, is looking outside the cancer, not outside the box, but like outside the cancer, and saying, why don't we ruin the cancer's environment, or its niche, or its comfort zone, and then hit it with various drugs, rather than come in straight away and hit the cancer. Let's make the cancer a bit uncomfortable.
I think that makes a lot of sense. So what are the ones that the cancer likes? You said surrounded brother.
Oh, there's lots of them. So recently we had one called NID2, one was called Perlecan, two different postdocs in my group, so people that finished their PhD. They're both worked on completely different projects, and then they started finding that Perlecan binds NID2, so it's like quite often people working in completely different areas find the similar molecules that also touch each other, and so we're starting to find a few common denominators that the cancer really likes. So here at the Garvan, we're trying to make antibodies now to block those molecules, certain aspects of them, so we can, you have to remember that every single molecule we talk about has an absolute function naturally in the pancreas or the area. So we need to know which part of that molecule the cancer likes. So you might block one aspect and keep the other aspects okay so that the pancreas is still functioning.
And you can do that.
Yes. Yeah. Which is amazing, right? Yeah.
How long have we been able to do that for?
I think we've been able to do it for, that's where all those immunotherapies kind of came from and those aspects. But for me to be able to be involved in that outside of a biotech company or a big pharma, it's very recent and it's something that we're really focusing on here. But usually I would go to a larger biotech company, etc. And so that's quite often, that's another thing that my group started doing, understanding the fundamentals of the disease first. Then quite often you need to partner with a big biotech just to get the ability to actually make truly translatable antibodies or truly translatable drugs that we can actually put into patients. And so in the last 5 to 6 years, we've managed to do this for multiple targets that we've identified here. That's amazing. That's a lifetime goal to be able to do that.
Well, you've done it. You're saying you've done it?
Yes, and they're in patients right now, being tested right now. Had a meeting about one this morning, and it's amazing to do this here in Australia, but also internationally. And so, you work on these things, you publish the paper, you hope people read it, but then when you start working with people that can actually make drugs against that, or quite often who have already made a drug against that molecule for a different reason, and then you can show them how it works. So those trials are ongoing for the last couple of years, so I've only started my group here since 2013, really. That's not very long, not very long. And those things are now being translated, so I didn't think that would happen in my lifetime. You think...
And you're still a young man, so it's like,
Not sure I'm that young anymore.
trust me.
Yeah.
In your lifetime it's happened, and you and Tree?
And Tree as well. Tree is also... I'm just a scientist. Tree is a scientist and a medic, so he can see both angles. I quite like that. So he can approach a problem from purely fundamental understanding, but also he can say, actually, I'm going to look at the actual clinical problem and angle in there. And so that's what I've learned now, to actually team up with medics in the area that I work in way earlier than I used to. I used to work on something, then explain it to a medic, and then they would say, well, that's wonderful, Paul, but we can't ever do that for a patient. And so now I can actually be a bit more educated as to what would work for a patient, what could happen. And so see that idea of breaking down that dense fibrotic tissue? That was crazy. Like, imagine telling a patient, you've got pancreas cancer, I'm going to give you your chemotherapy next week. And now we're suggesting don't give them chemo. Give them this drug to soften the tissue, to open up the blood vessels, to change the environment and delay their chemotherapy. It sounds mad. You then give their chemotherapy after that, and the chemotherapy works much better. So you need to push the ideas, but you also have to work with medics that say, that's not really going to work, I don't think we can do that. It didn't take many years until we can now do that, and that's now happening. And I think the reason that was allowed is because pancreatic cancer is just so deadly that we need to change our current ways of targeting this disease. So people are much more open to that.
Well, I was always told it was a death sentence, pancreas. 7 6 weeks and then you'll be done.
Yeah.
But and it hasn't moved much from that.
Like it's on average, I think it's still around the 90% of patients will die within that first year, which is devastating. I think it's a bit less than that now, but that's just not an acceptable statistic, is it? No, and we need to change that. The 5-year survival since I've been here has moved from 5 to 13%. That sounds amazing, right? It's more than
Well, it's
tripled,
over
almost
doubles,
tripled.
so,
Yeah,
yeah.
it's almost tripled. My math isn't good there, but what's happened there as well is, remember I was talking about the hallmarks of cancers. Say you take a pancreas cancer, and again I'm simplifying it. Imagine if we thought about them all. Every single patient gets the same drug. One drug fits all. It's not. We're now thinking completely different. 10% of patients don't have this problem. 10% of patients have a different hallmark, different hallmark, different hallmark. So if we can personalise medicine, and we can actually start identifying these molecules. So for example, one of those molecules I was saying, there's about 12 to 13% of patients that have those issues. That used to be overlooked, saying not good enough, there's not enough patients, it won't work. But now if you can identify them and say, I'm going to go after those 13%, can you imagine if it made a difference to those 13? And then we add it to our 13, and then we've now doubled the current situation. And also being aware of what you cannot do and what you don't know yet is very important in science, and I think that's coming back to that.
Extrapolate a bit on that.
Yeah, that's coming back to that idea of we don't know the answer, or we don't know, and it's okay not to know. So if you say 13% have got this problem, 20% have got this problem, and there's a whole bunch that we still don't know, you can then go, I'm focusing on these two, and that's what's great working in a team, because if you've got a large enough team of different expertise, the other part of the team's going after the part that we don't know, and then suddenly we find another 7%. And so we just start breaking away. Imagine a wall, and you just start chipping away at it and saying, right, one brick's gone, another brick's gone. So I think that's what we'll do in this disease, but it's also the same case for many, many cancers. And I think being willing to say that I don't think we're going to get a drug that affects every single one of those pancreas patients. And we're just talking about pancreas specifically here, but you know, there are so many different variations just within the pancreatic cancer patient cohorts, so we need to go after that. And that fibrotic thing I said, not all patients have that, right? They don't. And so we need to admit that and say, okay, so these patients, give this drug. But the beauty of what I told you before when I said we go in with the antifibrotic first, then the chemo, what we found was that if you give patients chemotherapy, 1 dose, 2 dose, 3 dose, just before their surgery, every time they do that dose, it causes death of the cancer cells, lots of them, but there's a big wound healing process, and it creates fibrosis. So every time you give chemotherapy, you're creating that fibrosis. So technically, even if there's patients that don't have this big dense tissue, as you give them chemotherapy, they will inevitably start forming this barrier, forming this fibrosis. And so if you wait too late, you can't break that down, right? It's inevitable, it is coming. So that's our argument, which was, if you just give it to every single patient, then those that have got fibrosis, you need this drug, or it should work, right? We still don't know. And those that don't, after a few rounds of chemotherapy, they're definitely going to get fibrosis, and so that drug needs to be there. So it's almost like blunting the problem before it occurs. Does that make sense?
Yes, it makes sense. It's the order you apply it.
Yeah.
Isn't that what happened with Professor Scollier, and the order in which he applied for the brain cancer?
Yeah, I think so, and I don't know the details there, but yeah, the order in which we do it is very important. So two of the trials we're doing, one is we're just not allowed to give it to patients until they've failed. And I can completely understand that because,
First do no harm.
you know, exactly, perfect, right? But then is it too late, right? And then the other angle was to actually go in early. So it's a wonderful opportunity to actually be able to say which one is correct. And as with everything, I don't think there will be a simple correct or wrong answer. I think there'll be nuances there, but we'll learn from that and then say, well, this is how we should start to treat that. So I just think, yeah, is it all in the timing? So cancer, we have to think of it in a few kind of ways. The cancer cells, don't just focus on them, think of their surrounding. So that's space, I guess, right? Spatially. What does the cancer do to its surrounding environment to allow it to grow, to allow it to spread? So that's kind of space. So we're actually saying this dense tissue is protecting it, but also space and time, right? Timing. It is so simple, right? I mean, someone in primary school, my son, could tell you that the timing of various different drugs would probably make a complete difference. It's very time consuming to go in and look at that in detail, but it actually makes a lot of sense. Like, you don't need to always give as much drug or two drugs together as much as possible. And the beauty is this really short pulses of antifibrotics is very subtle. We don't want that collagen to disappear completely. We just want it to relax. When it relaxes, blood vessels open. We can pump more drug in and we can actually get much more response. Or also in many cases, the drugs are very toxic, right?
Yeah.
You can get more response for less drug. Now, do no harm, as you said, right?
I don't think it was me, actually. It was Hippocrates.
Yeah, but, you know, we have to think of the patient as well, right? We need that quality of life, and many of these drugs you can actually take them from home, so that means that you're not sitting in a hospital. That's the idea anyway. I don't think the trials do that right now, but it is a pill that you can take beforehand. But again, I won't talk about the details of those, but it's like the fundamentals of those are the fundamental things that we are going after and saying time and space, just simple things like drug timing, makes a big difference.
Well, it's a lot of professors we've been speaking to are echoing what you're saying. It's about almost bespoke cancers. There's not one cancer. There's no such thing as one cancer. You've got breast cancer, you've got breast cancer, but they're all different.
Yeah.
But they just happen to be in the same spot.
Yeah.
So what you're saying, I guess, is tailor-making a immune response within that specific human body to that specific cancer.
Yeah. Yeah, exactly.
Yeah.
And so it's, you know, we call it personalized medicine. It's very difficult, and it's very difficult to actually justify why we'd go after such a small population of 5 to 10%. But if you actually take a step back and say, well, that's just for that aspect, we'll go after the other 10, the other 10, the other 10. It doesn't take that much until we're at 100%, right? I think that's where we want to be. But I love the idea of watching the disease evolve in real time. Make a movie. Just make a movie and watch it. Send it to an expert that's worked on it for years, and they'll typically be amazed at what they see, because they will be like, that's not what was supposed to happen, or that's not what I expected. And I like to be naive. I'm pretty good at being naive. Because you then become unbiased and you just actually report what you see. I love to talk to different experts and talking to people in general. I love doing. So you can learn, and then you can actually say, oh, we should have given the drug like this, or this would mean that we've been doing it wrong all these years. Or we've been doing it, it's wonderful what we're doing, it was right, everything was right, but very rare do we see that.
Well, and how many things happen via serendipity?
Yeah.
Yeah. I wasn't looking for that, but look, I found this.
Yeah, exactly. So yeah, that's what we do here. And the imaging aspect is, I think you need to also understand who you are as a person as well. I'm very visual, very, very visual person. Like somehow I just memorize cells. They look interesting to me, almost like they've got personality and stuff. And from being a visual person, watching a disease in a visual way, and reading out the actual results of saying that drug is working or isn't working over in this area, but over in this dense area, we need another drug. That it's just really intuitive to me. It's just like Netflix for cancer.
Well, yeah, it's a cool analogy. I mean, you're making me think of those people who can physically see music. Have you heard of those?
Yeah, I'm not sure on that, but I do have an
Well,
abnormally geeky care about when I've seen a cell. I can months, years later, I can still be like, oh, there was a cell that did this and did that, and that's quite a strange thing.
It's good recall on cells because you can identify different ones. You can see.
Yeah, and also the physical shape of a cell tells you a hell of a lot about what that cell might be doing, is doing, or is about to do. Another thing we did previously was we made fluorescent cancers that each cell talks to itself like a zipper. And rather than just calculate how much of the zipper there is, you can actually, if you make a movie, you can watch that the zipper constantly moves like that. And it turns out that how often that moves, and this is just molecules moving, you can predict that that tumour cell that is not moving, has not yet moved, is about to move, i.e. it's about to unzip and it's about to move. And so the idea then would be that if we could do that, we can actually give the drug before the movement, reduce the spread, and then also give the chemotherapy or whatever drug it is you're trying to give to kill. If we just go in and try and kill on its own, we might actually smash the area up, destroy lots of cancers, which is wonderful, but some will dissociate and then spread, and that's where we're in trouble. We're in trouble in both situations, so I think you cannot ignore one, or you can't go after one without the other, unless you're lucky enough to have a tumour that doesn't spread or move. But that is not usually the case in pancreas cancer,
Just some bang.
or breast cancer, or prostate cancer.
What do you love about this? What do you love about doing this job?
I don't know. I mean, I think that I've said this before. I don't think I've worked a day in my life. I don't have a rule of when I come to work. I don't have a rule when I go home. That sounds really relaxing, but it isn't, because it never switches off, really. Some days you'll work really late. Other days it's probably best to go home and go for a run. I love working with lots of different people with completely different ideas. The turnover of people as well is amazing. So, you know, you probably work with the same people for 4 or 5 years, some 10, and then there's a completely different crew. Some solid people that you constantly work with. But I love just going in somewhere, discovering something that no one else has seen before. And then it's up to you to describe it the best you can, explain it, and then find people that can help you. And it's one of those jobs that if you're in Sydney, you're not thinking, can I get someone from Sydney or Melbourne to help me? It's like, there is nowhere on the planet you won't ask, right? So we work with people in Finland, we work with people in Scotland, obviously, with my accent, America, there's so many countries and so many places, and so it's limitless who you can ask for help. And like-minded people will come in and they'll love that as well. They want to help, right? As I get older and I've been in this game longer, the collaborations with different people was much more intense, much more enjoyable, and much more like, what is the bigger picture, right? And that translational aspect is amazing, to actually take something and put it in a patient. You know, it's very academic at the beginning, and then one day you're like, this can go in a human being and possibly make a difference. And even if it doesn't, some bright spark will come and look at what I've done when I'm well and truly dead, or whatever people have done here at the Garvan or in any other place, and just said, you didn't look at that right, you should have done this. And isn't that great as well, you know?
Well, it's like Fleming and, oh God, Fleming found it, but Florey, what, no, don't tell me you're laughing,
Yeah.
it's like, was that a correct take on penicillin?
No, I'm just thinking it's funny that to have that in the same sentence as interviewing me, but that's all. No, but yeah, exactly, it's the serendipity again, and how one person perceives something completely different. Yeah, we have a mouse right now. I'm not sure if I can see these words, but we have a mouse
Well,
right now.
If you can't, we'll take them out.
Yeah. But our newest biosensor is part llama. So llama or sharks make completely different sized antibodies, so you can actually use those as biosensors, or even drugs actually. But that came from talking to someone in a completely different field, and we're using that to look at how chemotherapy works, and how we can improve chemotherapy. That's what I started on. But when I show that to Tree, who also runs the centre, he's not interested in that. He says he can watch immunisations and how they efficiently work, like completely different biology that I would ever imagine that we could look at. And so that's great. And so can you imagine then working on not just one disease? So I'm known as a cancer researcher, but like there's a lot of other papers and things that we've done that are nothing to do with cancer research. But people still have many other diseases, and so
That's still research.
it's still research. Yeah, and I mean, why wouldn't you go after something else? And that's the other thing that I learned from a very early stage of setting my lab was, once you've made these biosensors or made these tools to watch different aspects of a cancer, we give them out to anyone that wants them for free, and we don't really care what is done, because once you've made that tool for your purpose, for pancreas, say, there's people that can work on completely different cancers that you'll never work on. People are using them for looking at Alzheimer's, various different diseases that I would never ever work on, and that's one of the greatest aspects. And then one day, like 4 years later, they show you what they've achieved, and you're like, never in my wildest dreams would I have used it for that. So that's
a lot of things that have, that's like drugs in the past and thinking, anyway, we're going down a
like
rabbit hole there.
yeah. But you're right, like drug repurposing, right? Once we've got drugs for one disease, we can still rapidly put them to the next. Even if you prove that you can repurpose it, there'll probably be things that the drug's not perfect for, and then you start making a better version of that. But guess what? You've just had a kickstart to know that it really is making a difference. You're not starting from a blank canvas. It's like you've got something that's kind of working. Let's take it a bit further.
So I've got to ask you again about the Australian Cancer Research Foundation, and what's it done here?
Yeah.
This might not go in, but
Yeah,
I'd
yeah.
like to hear it.
No, that's good. Yeah. Like, so ACRF,
And could you say the Australian Cancer
okay.
Research?
Yeah.
Because the audience might not be aware of it, because we're not
okay.
selling it as a corporate film.
Okay. So the Australian Cancer Research Foundation helped Tree and I truly get together and go places that we couldn't have gone individually. And we were struggling. So when I started my group, Tree started his group, we both had microscopes that Trees could go deep enough and mines could go fast enough. But it just wasn't seeing all these kind of you know, the dark spaces, the spatial aspects, the temporal time aspects of cancer, how best to give a drug, can we look deep inside the abdomen? We just couldn't do that. And quite often when I was making movies, like when you take a picture on a beach and someone whizzes by on a bicycle and they're out of focus, people would ask, what's that? And I would say, well, that's probably the immune system, but we just can't image that yet. We're not fast enough. And in the era of immunotherapy, Tree and I getting together said, actually, if you put two of our brains together and our teams of, you know, the immune system and cancer, we can actually help each other. So we then started making microscopes that don't exist, right? And bespoke microscopes just so that Tree can go further and deeper inside the bone, and that I can go faster and see these kind of immune cancer cell interactions and all the kind of things that we dreamed of but we couldn't do before. We also had physicists, and we still do, who are looking at the images we're taking and saying it's still not fast enough. Or when you're looking at live tissue, imagine looking inside a pancreas in a living, breathing situation. There is so much movement, and we're trying to look at a molecular level. You know, it's impossible, right? So we've got people who are coming in and doing that kind of stuff, and that's what the Australian Cancer Research Foundation also funds. Those experts that not only look at the current boutique microscopes we've got, but make them better, make them faster, and actually allow us to go where we just cannot buy commercial systems. They just don't exist. So it's fantastic to be ahead. It's very scary to be ahead, but then you can actually breathe a little and you can be a bit more ambitious.
Do you think AI is going to help you with it?
Yeah, we're already using AI for that exact thing. So you and I, let's go back to that fibrosis effect. So if you think of fibrosis like, you know, meshworks of collagen, you and I can probably see X amount of structures and then it's gone. It doesn't look any different to us. But we've used AI, and we can definitely now see stuff that is so subtle that you and I can't see, automated, and it will do this overnight while we're home and in our beds, and we can come back in, and we've actually now shown that some of these structures can predict likelihood of response to a treatment. That's our idea, or likelihood of highly aggressive disease versus not so aggressive disease. So again, comes back to that unbiased aspect, doesn't it? Like AI isn't just looking for what we know or that we conceive. Something that's curly or straight, you and I can clearly see that, but there'll be subtleties within that that are completely different to AI, and that's what we're seeing. So that's in the last 4 or 5, I would say in the last 4, maybe 3 years we've been doing that.
Well, that's nothing.
That is nothing. We've yet to publish it, but it's there. And it's working.
Since COVID. Post-COVID, almost.
Pretty much, yeah. Exactly.
Which is like yesterday.
That's another cool thing. Yeah, that's another cool thing about the Insight Centre, or the Australian Cancer Research Foundation Insight Centre. One of the things they wanted to know was, in a COVID world, because that's when we got this grant, they actually said, well, can it be COVID protected, as in can other people use this, or do you have to work here? And we've now got it set up that there is different institutes all over Australia and even internationally that can actually use our team and do experiments without actually physically leaving. And the AI aspect as well is you can send those images anywhere in the world and have them analysed and tested without actually having to move.
It's very exciting.
Yeah, super cool. Yeah.
And going to get better.
I think it's just going to get better and better, yeah. But you still have to think of the ideas, think of the questions. But yeah, AI on simple images not just chat GPT.
It's just topical at the moment. I'm very happy with it. Is there anything else you want to say?
No, I think that was
Philosophically or
definitely not.
to encourage people?
No, it's good.
Yeah, I'm good.
Steve, do you have any questions?
No, that was really clear. It's good.
Oh, that,
Really clear. He doesn't say that to most people.
does he not? Alright, cool. I got lost there. I was just in a dream.
Yeah.
It was like a chat.
When you came back,
Yeah, hopefully.
it was a good dream. We enjoyed your company.
Yeah, thank you guys. Yeah.
Yeah.
Alright, awesome.
Awesome. You were awesome, mate. Thank you. Well done.
Cheers, mate.
Outside. Hold it exactly what we're doing. Like that. Okay. All right, Stuart, so we're rolling now.
Yep.
You're good. And action.
Okay. You ready to explain what's happening the way
Sure.
you did before? Okay.
Yeah.
In your own time.
I just say it to you guys.
Yeah.
Ah, okay. Okay, right. Now I understand. Right.
Okay, and set.
Okay, so here we can see in purple that fibrotic tissue, and you can see the immune cells rushing into a wound. And so you can see that if we could manipulate this fibrotic tissue, you could imagine we could improve immunotherapies in pancreatic cancer, for example. And again, by imaging this, we can see how much is too much and how much is just right. So it's a really dynamic process, and it's constantly evolving, and I think this is something that we've overlooked in cancer for many years. Over here, in red, we've got quantum dots, which looks at blood vessels, so it's quite intuitive. In green, you've got the cancer cells, and again, you can quite often see that in areas within a tumour, so there's 4 areas here, 1, 2, 3, 4, you can see great drug delivery, for example, in these 3 situations here. However, when you've got lots of this collagen or this fibrotic tissue, the blood vessels are all collapsed, the tumour has not been delivered any chemotherapy, and so we're never going to have any real chance to kill that tumour. So if we can start to manipulate the purple fibrotic tissue surrounding this, we can improve the chemotherapy, we can improve the response, and at the same time, you can see that these cells are actually migrating and moving along this collagen matrix, I guess. And so you can imagine that this could not only improve response, but stop the tumour from actually attaching to this collagen and spreading throughout the tumour. Done?
Excellent.
Right, now for the next angle. Tell.
So, the
And
next angle. Take 2.
gotcha, thank you. Focus there, done? Yeah, I'm just gonna rough that over. Rough that over, yeah, okay. I'm monitoring it. Set.
When you're in your own time.
Okay. So here you can see the fibrotic tissue surrounding the wound, and you can see that the immune system can quite easily move into this, using the fibrotic tissue to actually traverse and actually escape the tumour. In the second situation, you can see the blood vessels, you can see the fibrotic tissue protecting the tumour, and what we can find is that if we could reduce this fibrotic tissue, we can improve the drug delivery to those areas which are not being delivered any drug and therefore will not respond to the chemotherapy. That was really fast.
That was really good.
Amazing. Can we do it again?
Okay.
I'll make a tighter shot. Keep rolling. Rolling, still
Keep
rolling.
rolling.
Hang on a sec.
Okay, so here you can see the fibrotic dense tissue, and you can see the immune cells traversing along this dense tissue, and actually this is how, for example, cancer cells could actually move out of the tumour. In this situation, you can see blood vessels, and you can see that in certain areas we can have robust responses in drug delivery.
Sorry.
Sorry.
I just had a technical hit. Sorry.
I feel sorry for maybe people.
It's good to help yourself with the third,
Is that?
and in your own time.
So here you can see the dense fibrotic tissue. You can see the immune cells traversing this tissue. The cancer cells also use this to actually escape and actually start spreading throughout the body. In this second image, you can see blood vessels where we can see drug delivery in certain areas of the tumour, but there's many areas where there's poor drug delivery, and if we densely treat this fibrotic tissue and reduce that density, we can improve delivery. I said that shit at the end. Can I do that again?
Yes.
Yes?
Last time.
Here it is.
Alright,
Don't back yourself in the corner.
here we go.
So,
So here you can see immune cells traversing across the fibrotic dense tissue, and the cancer cells also use this to actually escape the primary site and spread throughout the body. In the second image, you can see the blood vessels here. We can see drug delivery in various areas of the tumour, but other areas, that dense fibrotic tissue is acting as a barrier, blocking drug delivery. So if we can target this first, we can improve the drug delivery and improve response in this deadly disease. Done. Let me go to the pub.
no, don't want to do it. Cap. One more shot to do. Rolling up.
Sweetie.
And camera set.
Sorry, clapping.
Mark. Good. And. Okay, thanks, Paul.
So I'll just say the same thing.
Yeah.
So here you can see the immune cells traversing along the dense fibrotic tissue, and cancer cells use a similar mechanism to spread from the primary site all around the body. And in the second situation, you can see the blood vessels here. You can see the purple collagen tissue, and you can see drug delivery here in these three images. And in this one, you can see the dense fibrotic tissue acting as a barrier and not allowing that to actually deliver. So if we target this, we can improve drug delivery in this situation.
Let's just. I'll just.
Still rolling.
Still rolling. And if you.
Mm-hmm.
Okay, that's the one left. Okay, and you ready?
Yeah. So here you can see immune cells traversing the fibrotic tissue, but what we also know is that cancer cells can also use this to actually spread throughout the body. And so this is something that we want to target in this disease. And in the second image, you can see the blood vessels in red here and the cancer in green. And down in the bottom here, you can see the dense fibrotic tissue, which if we target this, we can stop it being blocked from targeting the tumour, and we can actually improve the tumour drug delivery. I change it every single time, don't I?
It's good though. It's very good. Spooky.